Session for this Tuesday morning out here at Breckenridge at the Glenn Gerberg Weather and Climate Summit. This next presentation is particularly interesting as well because last year, as I mentioned before the break, we had a presentation on a dual polarized Doppler radar and how the Doppler radar was getting retrofitted and what we were expecting to happen as far as radar performance for helping the warning process and the forecast process over the short term. So this year we have Clark Payne from the Warning Decision Training Branch from NOAA's National Weather Service out in Norman, Oklahoma, to talk about using dual pol to your advantage. So he'll be going through a lot of case studies and also making it interactive for the audience here to look at the radar data, give some input, almost like a dual pol operational workshop, so to speak. Before Clark comes and speaks, I'd like to give you a little insight into dual polarized Doppler radar, and this is a video that was produced that has a little bit of fun times in it. So enjoy this, and then we'll start the presentation with Clark. Let's take a look.
Traveling through another dimension, a second dimension, where the difference between a snowflake and a raindrop can be clearly seen. You're moving into a land of both vertical and horizontal of things in the atmosphere. You've just crossed over to the dual polarization zone.
Welcome back, everyone. I'm Kat Taylor. Now, you might be wondering, what is dual polarization? Well, allow me to explain. You've probably seen them around. You know the tower with the white dome? They kind of look like a giant golf ball. Well, many of those house Doppler radars. About 20 years ago, towers were strategically placed across the country, giving forecasters a better view of the weather. Since then, the radars have been continually improved. But now, it's major upgrade time, and that's big news for forecasters and for you. To help explain, we've put together a couple videos that spoof our favorite commercials. Enjoy!
Honey, it's really coming down heavy. I wonder if it's going to flood again.
When my husband asked about flooding, I knew who I could talk to. The National Weather Service told me about dual polarization technology.
Conventional radar can detect the rain. Dual pol gives us more information about the size, shape, and variety of particles in the air. By sending and receiving both horizontal and vertical pulses, we'll get a better idea of how much rain is actually falling, which will in turn improve flood forecast. Other effects of dual pol may include better severe thunderstorm warnings and improved transportation safety. If you experience rain lasting more than 4 hours, check for local warnings in your area.
We know we'll be ready if the floods come.
And that's a good feeling.
Attention forecasters! Is your weather radar picking up more than just the storm? When birds, bugs, and bats show up on your screen, all that clutter can be a huge bummer.
I just want to see the weather.
Well, now you can. Introducing Clutter Cleaner. Powered by dual polarization technology, Clutter Cleaner works fast and efficient to remove biological matter, leaving you with a clean screen showing just the weather.
Wow, it's beautiful.
But wait, there's more. This revolutionary technology is also great for seeing flying debris in a tornado.
That would come in handy for those nighttime twisters. But wait, won't we have to replace our radar?
No way. With a simple upgrade, you'll be using Clutter Cleaner in no time. Clutter Cleaner, keeping your screen clean so just the weather is seen.
That's pretty awesome. Well, we're out of time, but it's not so bad. You can get all the details on this new technology at our website. Plus, don't forget you can keep up with us on Facebook and Twitter. Until next time, I'm Kat Taylor. Thanks for watching That Weather Show.
All right, am I better now? No, I can even hear myself through there. So, all right, well, what I want to talk to you all today about is dual pol, as you saw there. And I just want to show you how you can use dual pol to your advantage. And so what we're going to do is, how many of y'all know about dual pol? Obviously before this, how many of y'all heard about dual pol? Okay, how many of y'all have taken some type of training course or something on dual pol? Okay, so roughly most of y'all in here. Okay, what we're going to do is we're going to briefly review what the dual pol products are that you are going to get when dual pol is upgraded. And then the rest of the time, and that's only going to take maybe 10 minutes that we're going to do that. We're going to go through it very quickly. But then the rest of the time, we're just going to look at case studies. And what I'm going to want you all to do is looking at the normal stuff that you are used to right now, reflectivity, velocity. I would say spectrum width, but I'm not going to show any spectrum width. But reflectivity and velocity, I want you to tell me what you all see. And then what I'm going to do is I'm going to pull up the dual pol stuff, and I'm going to show you how dual pol would have made your decision easier or better in that case. So that's going to be the majority of our time here. All right, so what has and hasn't changed with dual pol? Well, since dual pol is just an upgrade to the radar, it's not actually changing the radar out or anything like that, all standard limitations still apply. You're still going to get beam bending. You're not going to have accurate beam heights. You're also going to have cone of silence. You're going to have VCP changes, your VCP limitations. All those things still apply with dual pol, so that's not going away. What dual pol is, and as you saw in that little infomercial right beforehand, was that with conventional radar, what we first did is we sent out just a horizontal pulse, and then we listened to that in that horizontal pulse coming back. What we're doing with dual pol now is we're sending out both a horizontal and a vertical pulse, and we're listening in the horizontal and vertical. So with conventional radar, we were kind of getting a one-dimensional picture of what we are seeing on radar. But with dual pol, now we're going to get kind of a two-dimensional picture. So we're going to be able to tell more of what's going on with the radar at that time. I say here, don't confuse that with phased array radar. Just because we're sending out two pulses doesn't mean we're getting more information. Phased array is going to be something that's going to be coming down the road a little bit later. And phased array is going to be the one that gives you more rapid updates. But dual pol is not going to do that. So with dual pol, you're still going to get your reflectivity, velocity, spectrum width products that you're used to seeing. But then you're also going to get what's called the correlation coefficient, or CC. You're also going to get differential reflectivity, or ZDR. And then the last one is specific differential phase, or KDP. All right, so what is correlation coefficient? In a nutshell, it is a measure of the similarity between the horizontal and the vertical pulses from pulse to pulse. Okay, what all does that mean? Well, if you look at non-meteorological echoes such as birds, insects, ground clutter, things like that, from pulse to pulse, your horizontal and your vertical channels don't behave very similarly. It's very chaotic, very complex scattering. And so your correlation coefficient, or your CC, for non-meteorological echoes, are going to be less than 0.8, roughly. And in fact, it's usually going to be much lower than that, but 0.8 is kind of our threshold that we use. For meteorological echoes that are non-uniform, such as hail or melting snow or a mixture, rain, snow, sleet, things like that, your correlation coefficients are going to be a little bit higher. They're going to be roughly 0.8 to 0.97. And that's because you still have some complex scattering, but not near as much as you had with the non-meteorological echoes. And then in situations where you have pure rain or pure snow, this is kind of our uniform meteorological echoes, your correlation coefficients are going to be very, very high. They're going to be almost near unity. And that's the thing with correlation coefficients. You're either going to have a value from 0 to 1. And the closer you are to 1, the more well-behaved the pulses are. And so with pure rain, pure snow, you're going to have correlation coefficients that are very close to 1. So here's kind of a typical values chart. And in fact, Dave, do you mind passing out those? I'm going to give you all cheat sheets, as I like to call them, or as my boss likes to call them, job aids. They're not cheat sheets. You're not really cheating. You're kind of helping yourself out a little bit. But what he's passing out here, and for those of y'all that are online, you can actually go to wdtb.noaa.gov, and you can look at this yourself as well. And it's called the dual pole decision aid. And what this is I've broken out each of the different types of meteorological echoes and non-meteorological echoes, and then giving you kind of the typical values of the different dual pole variables that you would expect with those different targets. So for example here, this is going to be a little bit different than what I'm handing out here, but what I'm showing here is for CC, you can see that for rain, hail, grapple, snow, your meteorological echoes, your correlation coefficients tend to be very high, usually greater than 0.9. You can see a couple instances where maybe if you have giant hail, it can go below 0.9, or you have wet snow, it can also go below 0.9. But for the most part, it's usually greater than 0.9. And then the other thing is, if you look at the non-meteorological echoes down here towards the bottom, you can see that your correlation coefficients tend to be much lower, less than 0.9, less than 0.8. Things like that. So you can see that correlation coefficient is great for discriminating meteorological and non-meteorological echoes.
Sorry, did you say it's a ratio between the horizontal and vertical what?
No, that's what we're actually getting ready to get into. CC is just a measure of the similarity, how they're behaving inside the pulse volume. So if my horizontal and vertical channels are scattering differently, then you're going to have a lower correlation coefficient. Whereas if they're scattering very similarly, then you have a high correlation coefficient.
Oh, between the targets within the scan, right?
I'm sorry, what?
So it's between the correlation between the targets within the scan?
Yes. Okay. Yep. So, and then differential reflectivity, this is where you have the ratio of the horizontal to the vertical channel. And actually, if you kind of do the math a little bit, it actually turns out to be the difference between the horizontal and the vertical reflectivity factor. And what this does is basically differential reflectivity is a great indicator of the mean drop shape of the dominant hydrometeor within the resolution volume. So, if I've got a spherical, awesome. So if I've got a spherical object here, like what I have here, you can imagine that your horizontal reflectivity factor is going to be very similar to your vertical reflectivity factor. And so if you take the difference between the horizontal and vertical, you get near 0. So when you have ZDRs that are very near 0, that indicates that you've got a spherical object, or that your dominant hydrometeor is spherical. If I've got a horizontally oriented target, then my horizontal reflectivity factor is going to be greater than my vertical. So if I take that difference, I'm going to get a positive ZDR. So a positive ZDR indicates a horizontally oriented particle. And then if I've got a vertically oriented particle, my horizontal is going to be less than my vertical. So if I take that difference, I get a negative ZDR. So vertically oriented particles will have a negative ZDR. And if we look at the typical values here, what you can see is that there's no distinction of ZDR between non-meteorological and meteorological echoes like we saw with correlation coefficient. But what you can see is that for rain, the higher your ZDRs get, the larger your drops are getting. For hail, what you can see is that for hail that's pretty uniform, not melting or not mixed with rain, your ZDRs are going to be very near 0. And in fact, if you get very large hail, you tend to get negative ZDRs. But then as you get a mixture with rain or you start to get small melting hail, your ZDRs can get very large. And then you can kind of just see the other things here with ZDR and the typical values. And then the last one is specific differential phase. And I told myself I wouldn't show you all an equation, but I'm going to show it to you, but I'm not going to talk about it. basically, specific differential phase is just the derivative of the differential phase between the horizontal and vertical pulses. And, you know, to just put your minds at ease, this basically is going to tell you how much liquid water content you have inside your radar resolution volume, or at the range band that you're looking at. The higher your KDPs, the more liquid water content you have there. So KDP is going to be a great indicator for rain, and heavy rain at that. Now, I will say that at S-band, or using the 88D radars, that when you get to values roughly about 4 to 5 degrees per kilometer, that is kind of your threshold for pure rain KDPs. That when you start to see KDPs greater than 4 to 5 degrees per kilometer, that's going to indicate to you that you actually have more than just heavy rain in there. You've also got some melting hail going on. And the higher those KDPs go above 4 or 5, the more and more of that small melting hail you have going on.
You've got rainfall, and you literally rainfall KDP?
No, you cannot. So, well, let me back up just a second. Yes, you can. If you are in the batch cuts, like kind of in your mid-range elevations, it uses the Doppler cuts to generate the dual pole variables, and those are subject to range folding. And if that happens, they get range folded, but technically you can't range fold KDP. So, but what you can see here is that for all the other meteorological echoes like hail, grapple, snow, KDPs aren't that significant. You usually don't get anything greater than 1. And then one other thing I'll also mention here with KDP is that when you start to get values greater than 1, that's a good threshold for heavy rain situations. So, all right, enough of the theory in the classroom. I want to start getting into the interactiveness now. So for our first case, well, here, let me just ask, are there any other questions as far as the products go? All right. Then we'll jump right into the cases. So this is from Branson, Missouri. This was back in February of last year. And we're going to be in the early morning hours. We're going to be talking about 1, 2 a.m. in the morning. So it's going to be a nighttime case. Here's the environment setup. You've got a very strong upper disturbance over Nebraska and South Dakota. That's setting up strong southwesterly flow aloft over southwestern Missouri, where we're going to be concerned about. And what you can see at the surface is a very strong surface low is set up with a warm front going through northern Missouri and a cold front stretching in through eastern Kansas. So we're kind of in the warm sector here where we're going to be concerned about. So storms are going to be very probable at this time. And if we look at just a couple of the environment parameters, if we look at instability, this is just low-level instability. And I jumped ahead of myself there. This is low-level instability. We have almost 1,000 joules per kilogram of 0 to 3 kilometer CAPE at this time. So very strong low-level instability. And coupled with that is very, very strong low-level shear. The 0 to 1 kilometer, I think this is effective shear here, is approaching almost 1,000 at this time, 1,000 meters squared per second squared, which is off the charts. So as you can see with my top bullet here, your tornado threat is high. So this is where I'm going to ask my first question. What, as a meteorologist, would be your biggest fear when it comes to tornadoes?
Getting hit by one.
An overnight tornado. What else? What else with a tornado is difficult when you're trying to get spotter reports and things like that? It's dark out. What? Fast moving. How about rain wrapped? Rain wrapped tornadoes. So nighttime, rain wrapped, fast moving are just all nightmares for meteorologists. Well, guess what? That's all that was happening here with Branson this night. And I'll give you a hint that what we're going to be looking at here, this is at a time later on in the event. There are already some tornadoes before. So they already had confirmation that tornadoes were occurring with this event. So you can imagine that anytime you start to see any more rotational signatures, you're going to be very concerned about what's going on. But over here on the left, I've got reflectivity on the bottom, and on the top I have storm relative velocity. What are some things that stand out to you all? Yeah. Yeah, so we got a nice velocity couplet. Looks like we've kind of got a hook right there, as you were saying. So how many of y'all are concerned about a tornado at this point? You can raise your hand. Yeah, I was going to say, I think everybody's going to raise their hand at this point. How many of y'all, just looking at reflectivity and SRM, are 100% confident that you have a tornado on the ground? It looks, I think the radar is about, this is just near Branson. It's in Springfield, so I'd say about 50 miles maybe. So.
The only thing that's missing is not seeing debris. That would be the only thing that I'd be looking for as well.
Mm-hmm.
Debris ball would harm it for me, but there's a lot of strong signal there.
Mm-hmm. So do you see anything that would indicate a debris ball in reflectivity or?
Not on reflectivity.
Not reflectivity?
At this point, I probably would be concerned there's one developing, but probably not touching down yet.
Okay.
Just looking at reflectivity and storm relative.
Okay. Yeah, so, all right, well, let me jump into dual pole here and just kind of. The what? Mm-hmm. Yeah. Yeah, so maybe even some wind and. Yeah. So if we jump over to dual pole now, and I'm just going to focus in on that velocity couplet. And what I would look for that would tell me that I've got a debris signature is, first off, I'm going to look at correlation coefficient, the product here in the lower right. I'm going to look for very low values of correlation coefficient or a local reduction in correlation coefficient. And that's because if I've got debris being lofted, it's not going to have any high correlation. I mean, you might have, 2x4s, insulation. I mean, you got all sorts of things, nails, cows, everything floating in the air, and that's just going to give you very low correlation coefficient. So let me ask you here, I didn't put any annotations on here, but we're just northwest of Table Rock. So we're right here where I've put my pointer. Do y'all see any indication of a reduced correlation coefficient? Nope. Nope. And then the other thing that you can also look at is look at ZDR. And because you've got 2x4s, insulation, things that aren't going to be oriented in any one particular fashion, your ZDR is also going to have a local reduction. It's going to be very near zero. So do you all see north of Table Rock, and I'll put my pointer there, do you all see a local reduction or very near zero ZDR at this point? So not a whole lot. I'm not even real confident at this point that there's a debris signature, but I am confident that I've got a velocity couplet, and I'm going to be ready to say something about a tornado at this point. That there's one probably developing, maybe one's already touched down. We don't know yet. All right, let me step forward to the next volume scan. And just looking at reflectivity and SRM, is anything changed in your mind? Anything different that you see here? Anything that would add confidence that there might be a tornado occurring?
Definitely have higher reflectivity near the velocity couplet.
Okay, so maybe right along in here.
Much higher reflectivity.
Mm-hmm. So right here. Mm-hmm. Yeah, ZDR has dropped. But just looking at reflectivity and velocity at this point, all right, how many of y'all would say you're 100% confident that that there's a tornado going on at this point? Raise your hands. No takers? No takers? Oh, I saw. Yeah. Yeah. Well, let's take a look at correlation coefficient right near the velocity couplet. And this is very important that when you are looking for the debris signature, that you make sure that you are looking co-located with the velocity couplet, and also that you are in high reflectivity. I'd say greater than 40 dBz. Just because when you start to get low signals, that can cause your correlation coefficient to drop. And so be wary of that. So make sure you're co-located with the velocity couplet, high reflectivity. So at this point, we are near the velocity couplet, we are in high reflectivity. Now I ask everybody, how many of y'all feel 100% confident that there's a debris signature? I think I see most people raising their hand. I see a couple not wanting to raise their hand, but yeah, I mean, at this point, I'm 100% confident that there's debris being lofted by this tornado at this time, and I might go on air, or as a Weather Service meteorologist, I would definitely include something in the product to mention that radar has confirmed a tornado is occurring at this time.
Can you just point out the values you're seeing there, because the scale is kind of hard to read.
Yeah, no, these values here, starting to get into the greens, we're starting to get around 0.8 or a little bit less. So we're getting into that non-meteorological realm. So, and then, just to add confirmation to what we are seeing, looking at ZDR, ZDRs are starting to become much lower, much near 0 dB at this time. So at this time, I am 100% confident that there is a debris signature going on at this time. So it's a nighttime tornado. It looks like it's rain wrapped. Right now, you've only gotten reports of funnel clouds from your spotters, mainly because it's nighttime. Too, it's also a hilly area. You are in the Ozarks right now, so it's very difficult to get spotter reports. But at this time, all you were getting were funnel reports. So this gave you added confidence and better confidence of what you were seeing at this point. So now I'm going to step forward a little bit. We're going to go a little bit quicker. How about here? How many people still think they see the debris signature? See a tornadic debris signature? Raise your hands. Okay, let me step forward again. No, the reason I think it's rain wrapped is just because of the reflectivities all around the couplet. Mm-hmm. So this is as it was moving into Branson, and you can see there was still an indication of, so this has been 3 volume scans now that we have seen the debris signature, and so this is something that you could be communicating to the public. Hopefully they wake up, but I mean, wouldn't this be nice to be able to wake up the public in the middle of the night and be confident at what you are seeing and not just be kind of thinking, well, maybe it is, maybe it isn't. I mean, you can definitely say, there's debris coming your way. So, all right.
By this time also in the town, are the sirens going off at this point?
You would hope so. They should be. Mm-hmm. Yeah, it's staying very tight, very tight. So, and I mean, I don't know what those values are there, but I mean, I think you're talking almost 100 knots of shear, gate to gate shear, which is just incredible. So, but which isn't surprising given the very low level storm relative helicity that we saw. All right, I'm going to step forward one more time. How many of y'all think you see the debris signature now? Mm-hmm. Exactly. That's actually the point I wanted to make here, is that your velocity couplet has disappeared, which probably indicates now that your tornado is dissipated. It's no longer causing damage, but debris doesn't just stop when the tornado stops. The debris is still floating in there, especially if you've got, you're in areas of trees. You've probably got leaves and things that are going to take a while to settle down. So what you're actually seeing here is you're still seeing debris in the air, even though the tornado is dissipated. So, that's one thing that's why I always say make sure you've got that velocity couplet. Let's say it's a tornadic debris signature, because you could still see the debris afterwards. So, you want to make sure that you're not saying, oh, there's still a tornado on the ground, because it isn't, but there's still debris settling at this point. So that's the kind of the summary here. The Springfield office was able to actually use this dual pole data to enhance their warnings their wording, which helped emergency managers and local media be more confident about what was going on. And this is being at 1, 2 o'clock in the morning. So I don't recall. Was there not? Oh, the question was there any fatalities?
Yeah, I believe there were 3 separate fatalities in Missouri from 3 different tornadoes in this event. I'm not sure if I think it might.
I'm sorry, but I do believe there were 3 separate fatalities in Missouri with 3 separate tornadoes in this event, and this may have been one of them. I'd have to check, but
okay. Yeah, I'm not for sure though, right off the top of my head. But this is just a cool pic that I wanted to show you all here. So that debris can get lofted pretty high into a storm, and this is actually a vertical cross section through the tornado. I don't remember exactly what time it was, but you can see here's kind of the tornadic signature here in velocity, and here's the debris that's getting lofted. And another case, this was back in May of 2011, Oklahoma City, just in northwest of Oklahoma City in Piedmont, had an EF5 tornado go through, lofted the debris to as high as 40,000 feet. And we were able to see that on radar, and it was just very impressive just to see what a tornado can actually do. What? Oh, what's? Yeah, this is correlation coefficient. Sorry. Yep. So, all right, that's the end of the first case study. The next one now that we're going to jump into some cooler weather. We're going to jump into winter weather now, which is appropriate given what it is outside. We're going to be in Long Island, New York. We're going to be, it's January 21st, 2012. We're in the late morning hours. Is that your birthday? So here's the sounding from Upton. And what you can see is that for the most part, it's very dry throughout most of the layer. But what you can see is the temperature is well below 0 Celsius, so all below freezing. So at this time, we would be expecting snow with this type of environment if we get enough moisture. Like I said, it's very dry. And this blue outlined area is kind of your snow production layer. It's at -10 to -20 Celsius. So you can see it's very dry in that layer, so you're probably not getting anything at this time. But let's look at it 12 hours later. Here's a 12Z sounding. And what you can see is you can see massive amounts of moisture have come into the area. You've got moistening throughout the whole entire layer practically. So in your snow growth layer, now you've got very moist conditions. And your temperature is still all below freezing throughout most of this part, but look at this area that kind of highlighted in red and just look at the temperature. And I'm going to step back and step forward. Anybody noticing a trend? Yep, developing a warm nose. So do you think we're going to stay all snow throughout this event? Yeah. No, you're probably not gonna stay snow through all this event. And in fact, the Weather Service forecasters at this point were anticipating a transition from snow to sleet, snow mixture to a freezing rain, things like that. So, how many of y'all would like to be able to tell on radar where exactly that transition is as you're going through? I know I'm asking a lot of leading. Yeah, I'm asking a lot of leading questions, aren't I? Let's look. Oh, and here's just the surface. Here's just the surface data, and what you can see is right. I know it's kind of hard to see from where you're at, but here's Long Island, and to the north we've got well below freezing temperatures, and just to the south we're right at freezing or just above freezing at the surface. So, so you've got some onshore flow. So, yeah. So here are the 4 products, and I've got reflectivity in the upper left, I've got ZDR in the upper right, CC down the lower right, and KDP, which we probably won't look at KDP much, and just ignore that bullseye. That was a data artifact at this time. But just looking at reflectivity, this is about 3 hours after that 12Z sounding, so you're probably still in, you might be anticipating some more warming going on at this point. But can you all see any indication of melting? A little bit? So, yeah, these higher reflectivities. Mm-hmm. So, and how confident are you? But be pretty confident. Yeah.
I'm mailing it in.
You're mailing.
It's sleep mostly, but you'll see that at 850 probably you're starting to see it.
Mm-hmm.
Right.
Yeah, and if we step down the correlation coefficient, what we're seeing is off to the north, we're still seeing pretty much all snow at this point because correlation coefficients are all very near unity. If we look at ZDR, if you look in your package, you can actually look at the snow page, and it's going to tell you that in snow and dry aggregated snow, your ZDR is going to be very near zero. So, you've got ZDRs that are close to zero here, and reflectivities are kind of moderate at best, kind of the 20 to 30 dBc. So and ground temperatures are below freezing. So we're going to be expecting snow in this area. But if we look down to the southwest, kind of in that area that y'all were seeing what we thought was a bright band, a bright band signature, well, correlation coefficient just confirms that for you. It is telling you this is a bright band. We do have some melting going on at this point. So what I'm going to ask you is where we've got this red cross, this red crosshair, is what do you think's going on right there at this time? Snow? Why do you think snow? Mm-hmm. Correlation coefficient's high. ZDR very near zero. Yep. I think I would agree with y'all here.
I'd say in the next 49 minutes.
49 minutes. I'm going to step forward 49 minutes and let's see what happens. Let's actually step forward though. And we're going to go forward. This is 1540. This is 12 minutes later. Yeah. Hey, we're meteorologists. We're not supposed to be exact, right? We're just supposed to be close.
This is what I said within 49.
Yeah. It's all about verbiage. What do you think is going on at that crosshair now?
It's changing over.
Mm-hmm. Melting snow. Okay, so you're saying still all snow, maybe maybe starting to change over. Yeah. Well, yeah, this is a. Yeah. No, at this point, you're definitely, I would say, starting to get that switch over. One thing to keep in mind with radar is that you can't really get real detailed with exact locations at the ground. Remember that you're actually sampling this above the ground. And so some stuff could be happening down below that could be changing things just a little bit. So, don't think that, right on this side of the crosshair it's this thing, and on this side of the crosshair it's this thing, that there is going to be a transition. It's not going to be a hard cutoff. But, yeah, at this time they were starting to see a switch over to sleet at this time. If we step forward, still the same thing? Still some sleet? Yeah. And I want to draw your attention now, though, to this area right here. What we're actually seeing is we're seeing a reduction in correlation coefficient, which is indicating kind of a melting layer signature here. Then your correlation coefficients go back up. And then they go back down as you get a little bit lower. So what do you think's actually going on there? Freezing rain. Yeah, what we're actually seeing is we're seeing a refreezing signature. We're actually seeing a sleet signature at this point, which is really cool. I mean, being able to see that on radar.
So you're saying as the coefficient is going, you got different stuff going on, and you actually are getting into a layer where, okay, now this is an area where it's uniform, as you said, but it's probably not all snow like it is north.
Mm-hmm.
Sleet.
Yep.
But isn't that more a function of the beam height as you move away from the radar?
It could be. It could be. And I'm going to caveat this with that we still don't know exactly what's going on here because there hasn't been a whole lot of research and a whole lot of in situ measurements to tell us exactly what's going on there. But we do believe that this is a refreezing signature. And what we think is that as the warm air is coming in, it's getting a little deeper, and now we're actually able to see two melting layers or see those two kind of transitions where the temperature is crossing the 0 Celsius line.
I have a question.
Mm-hmm.
I can't see. My eyes are burning old. Are we over dry land, the area that we're talking about?
No. Yeah, here's Long Island. This is the ocean here, and this is the ocean here. Mm-hmm. So this is Long Island. So this is land right here. We're just off the coast here with what we're seeing here, but this crosshair is right on the land. But let me just step forward a couple more, and you can actually see that refreezing signature become more and more prevalent as that warm air is moving further and further north. And so you still see that refreezing signature, and what do you think's still going on there at the crosshair? Sleet. Probably. Do you think it's more?
Playing into that, it's already been over its own water now for a time, so that's why you're seeing the refreezing at that point south of Long Island. We see this happen a lot.
Okay, where you get kind of that.
Where it refreezes again as freezing rain or sleet.
Mm-hmm.
It's a lot easier to see it on this than on conventional radar.
Yeah.
But
I was gonna.
The ocean plays into a fair amount of that south of Long Island.
Okay. Yeah, I was gonna say, how many of y'all are seeing? How many of y'all are seeing this in the reflectivity alone, or is dual pole really helping you kind of pinpoint what you're seeing?
I mean, is it kind of a phase of wet bulbing though? I mean, you kind of get that initial push.
It could be. Yeah, it could be. Yeah, one of the things that we always try to say with the melting layer signature that you see in dual pole is that it's really telling you where the wet bulbing is going on. Sometimes the melting layer signature may not be where your 0 Celsius is in the sounding because of wet bulbing. But I would imagine here they'd be pretty close because of just how moist the atmosphere, how saturated it is throughout the whole layer. But yeah, I mean, that is a good point. And then I'm just going to kind of step through here and just kind of watch the evolution as the warm air is pushing northward. And just how complex the melting and the refreezing is, and how dual pole is really kind of helping you pinpoint that stuff even better than just conventional radar was. So here you can see now you almost got that typical ring that's telling you a melting layer that's all around the area. But then you are seeing kind of these reductions here, maybe right along in here, that may indicate there's some localized refreezing going on. Yeah. When you're getting refreezing, it's actually going back down a little bit until it fully refreezes again. So because you've got a mixture of water and ice.
So after it's refrozen, it goes back.
Yes. Yep. Yep. So, and then again, it's very complicated what's going on, but dual pole is kind of hinting to you where that complication is going on. And so just to kind of summarize, there's dual pole data added information telling us where refreezing was occurring, and a lot better, I think, than just reflectivity alone. So, but I want to caveat this with that not all sleet events will be recognized, just because since it's a very low level signature, if your radar is real far away from this event, you're probably going to overshoot it and not be able to see this. So you've got to be very close to it at this time. There was, and I didn't get them put into this, but it was part of another presentation that we did where we saw that. But I think Long Island ended up getting. Oh, yes. Yeah, no, sorry. He asked if there was any surface obs or any observations to back up what we were seeing here. And yes, there was. I think Long Island, along there, they got almost 5 to 6 inches of snow with this event. But then it started switching over later. And in fact, at that time where you started to see that correlation coefficient signature come over the red crosshair, they were actually seeing the switch over to sleet. So it did give the forecasters added confidence at what they were seeing. Yes?
So in a truer dry bulb scenario where the low layers are really dry, what kind of signatures would you be expecting?
Ooh, that's a good question. I would probably expect to just see that lower correlation coefficient signature be closer into the radar because it's going to be lower than what we would be expecting based just off of the sounding. So I'd probably expect to just see everything kind of shifted inwards a little bit. And then, but I mean, if it got too far, if that got contracted in too much, then you might not see the two melting signatures. You might just see the one. So, any other questions with this event before we move on to the next one? All right. Let's move on to case number 3. This is going to be in Sacramento, California. And this is mid-March. And here's just kind of the quick environment setup. Freezing level is right at around 3,000 feet, so not too far off the ground. And there's a very deep trough coming into the area. And we're going to be looking kind of, I think Sacramento is right around in there. I'm not too up on my California geography, but it's a very cold air aloft, a little bit further north. Okay. Okay. Okay, so right along in here. Okay. Okay. We're gonna get exact here. No. Anyways, what you can see is you can see a very deep trough that's digging into the area, and it's allowing for very cold air aloft to come in, and that's setting up a very unstable environment for this time of year. So I basically say, let the storms begin. And just looking at reflectivity, what are y'all thinking?
Strong shower, maybe weak thunderstorm.
Okay, strong shower, weak thunderstorm. Anything else? Any other thoughts? As Greg said, looking at one thing, you can get a bunch of meteorologists and get a bunch of different opinions. So, if you do,
some of the areas in the reflectivity with some very high reflectivities.
Mhm.
A little hint, maybe some hail.
Maybe some hail. Okay.
We need clutter cleaner.
Yeah.
Can we buy that?
Well, I can help you out just a little bit here.
Okay.
You don't need clutter cleaner where you have the high reflectivities. I'll tell you that. Where out away from here, you're going to need some of that clutter cleaner, but you can see that with the correlation coefficients very low. You can just wipe that out. Ignore that. But let's look at the high reflectivity. Okay, I'm going to tell you what dual pole is telling us here. First off, if I've got high reflectivities and very low ZDRs, these are slightly negative, but I mean very near zero ZDRs, what's that telling you? Okay. Yeah, I mean, these are very slightly negative, so I mean, maybe a little bit of vertical orientation, but probably near spherical at this point. But I mean, yeah, I mean, negative is going to tell you that, but it's very slightly negative at this point. No, not big raindrops, because if you were thinking big raindrops, your ZDRs would be very positive. What? This is actually telling you that this is hail going on at this time. And correlation coefficients, if you're thinking hail and it's mixed in with rain, you're going to expect your correlation coefficients to drop. Well, your correlation coefficients are actually very near unity at this time. So this is actually telling you that you've got all hail with this storm, that there's not a whole lot of liquid precip at this time. And KDP just backs that up for you because KDP is not very high. So we've got a storm that has pretty much all hail, and it's all pretty uniform at this time. Now, I will tell you, as far as size goes, your size isn't going to be very large. This is going to be all very small hail, because large hail would have, again, a reduction in the correlation coefficient. So what we're seeing here is we're seeing a storm that's producing very small hail. Now, how much hail do you think is falling with this storm? What product would give you an indication of that? Mm-hmm. Yeah, reflectivity is going to give you a good indication, because if your reflectivity is not only size dependent, it's also number concentration dependent. So if dual pole is telling us we've got small hail and reflectivity is really high, the only way we can get reflectivity that high is if we have a lot of small hail falling with this storm. Y'all want to see what actually happened with this event?
The ZDR was telling you that it's hail because it was near 0. Correlation coefficient is telling you that it's all hail because it's near 1. What was the KDP telling you?
The KDP was telling me that there was no rain mixed in with this hail, that this was pretty much just all hail occurring. That if there would have been some rain mixed in, and that's the beauty of KDP. I forgot to mention that, is KDP is independent of hail. It does not get affected by hail unless it's melting hail. But hail, since it's very spherical in nature, will not affect KDP. But if you have hail and rain mixed in, the rain will contribute to the KDP signal. And so what we're...
Just knowing your low freezing level, you know, you could say, wow, we're going to have an accumulating hail situation here.
Yeah.
Yeah, I mean, synoptically, this is pretty common in the West, you know, to get that kind of a thing. But what, so were your KDP values above 5?
No, the KDP values here were almost near 0 for most of the event, or for most of the area that we're seeing here. So that's definitely telling us there's hardly any liquid precip at this time. And here's what happened. Lots and lots of accumulating hail. And I think this really here is around 5 inches. 5 to 6 inches of accumulating hail. It almost looks like it is outside right now. But this is, you know, and this is March, so I guess you might, you know, be convinced that it could be snow, but it's not. That's all hail there. So that's what actually happened here with this event. And dual pole was able to give the forecasters there added confidence that what they were seeing was actually accumulating hail and not hail mixed with rain or anything like that.
Was that 5 inches?
5 inches. Yeah.
How far away from the radar was it?
Let's see if we can... Not very far. I mean, this right here, I'd probably say 10 miles, maybe 15. With the what? No, I wasn't able to pull that up and look at that before coming here. So I don't know how high the echo tops got. That would be my guess too. So, but there's case number 3. All right, let's move on to case number 4. Now we're going to transport ourselves back from the West Coast. We're going to go to the Texas Panhandle. We're going to be in Amarillo, Texas. And this is April 11th. And here's the sounding here, and you can just see this yellow profile here is kind of your partial sounding, and you can see there's not a whole lot. I mean, the cape is very skinny at this point. It's not too terribly thick or too terribly what we'd call fat cape at this time. But you can see very moist throughout most of the layer here, except maybe a little bit drier down towards the surface. We've got almost kind of dry adiabatic and super adiabatic near the surface, so wind threat's going to be a little bit higher. And if we look at the vertical profile of the winds, we can see some turning in the low levels with very strong winds aloft. So this is just telling us, you know, we've got some deep shear going on, also got a little bit of low-level shear going on. We can also see that here looking at the photograph. And looking at just kind of at the surface and satellite plot, we can see there's kind of a warm front set up right along here where we see this red line. And that's kind of where the focus of the storms were initiating, was off of this warm front. And then here's just kind of a zoomed out, kind of high-level picture of what we're seeing with radar. And we're actually going to zoom in on this storm that I have highlighted here with the pink box. So just looking at reflectivity, what are your thoughts? You got a supercell? Yeah, you got the nice little hook echo, got high reflectivity gradient, got the high reflectivity core out ahead of it. So yeah, definitely a supercell going on. And just looking at the dual pole, what it's kind of telling me here is that these higher differential reflectivities here, higher ZDRs, is telling me we've probably got a lot of heavy rain going on with this event. There might be some melting hail in there, given the higher reflectivities. If I look a little further north, I do see a reduction in differential reflectivity, and that's correlated with higher reflectivity. So that's probably telling me I've got a little more hail there instead of rain. And correlation coefficients is telling me, yeah, you've probably got a mixture of hail, rain throughout most of this core, just because the correlation coefficients are low. And KDP is telling me you've got a lot of rain. Values are approaching kind of that 4 to 5 degree per kilometer threshold that I talked about again with just pure rain. So what we're looking at here is probably a lot of rain going on, probably some hail mixed in at this point. But that's not the cool part. What stands out to you here? KDP? Yeah, KDPs are maxing out at this point. Right now with the 88Ds, KDP is kind of thresholded at 10 degrees per kilometer. Values, if anything goes above that, it just caps it at 10 and just calls it good. Says that it's just 10 degrees per kilometer. What do you think's actually going on there? Massive hail. Yeah. Yeah, there's probably some bigger hail mixed in, but what I would say here is that bigger hail, when it starts to melt, it'll develop kind of a water torus, but it's not going to look like a giant raindrop. The only time you're really going to get those real giant raindrop looking hail signatures is if you get the smaller hail, but then it develops a water torus around it, and it makes it look as a real giant raindrop. Melting isn't as big of an issue with larger hail just because it's so large and it takes so long to melt. But with the smaller hail, you can get the signature. And that's actually what we're seeing is here, is we're seeing some smaller hail that's melting. Now, there could be some larger hail mixed in. And that's one thing I want to kind of bring across here is that don't ever try to just tunnel yourself into one decision here, that, you know, there could be multiple things going on inside that storm, but the dominant signal here is smaller melting hail.
But you can see it's a large area of hail.
Mm-hmm.
You got all
Yes.
those KDPs.
Yeah, yeah. So yeah, definitely a large area of hail, and it's all melting right now. And question? No, you're fine. Yes. Mm-hmm. Yeah, this is actually a good question because this is actually what we call non-uniform beam filling. It's just a data artifact that comes with dual pole, and this typically occurs when you either get a line of storms that align along a radial of the radar, or you get a very strong hail core, and you're kind of at mid-ranges to the radar. And what happens is you just get a data artifact that's called non-uniform beam filling. You know, and basically what happens is you've got hail at the top of the beam, and you've got rain at the bottom of the beam, and that non-uniformity of the hydrometeor types in there causes CC to just drop out and go very low. So it's just a data artifact, and until we can alter the laws of physics, we're not going to be able to do much there. But yeah, so when you see that, just note it as a data artifact. But looking at the KDPs here, you got a very large area of very high KDPs that are maxing out. And KDP is not only shape dependent, you know, it's also number concentration dependent like reflectivity is. So for KDPs to get that high, you've got to have a lot of melting hail at this point. So I'm going to step forward and just kind of watch the evolution of the KDP here. Still stays very high. And look at Masterson here and just look at the storm motion. So I'm going to step back here. I'm going to put my cursor right there. So storm is not moving very fast. You've got KDPs of almost 10 degrees per kilometer over this area that have lasted for 15 to 20 minutes at this time. So you can just imagine you've probably still got accumulating hail here. But guess what? It's melting, and it's also mixed in with rain, which tells you you've got accumulating hail with rain, unlike the last event that we just looked at. And then it kind of ends here. Y'all want to see what happened? Here's what happened. Here's this guy. This guy is standing next to a hail drift. These hail drifts got almost 4 feet in some places. And it actually ended up plugging up some drainage ditches and caused more flash flooding than probably what would have happened if we wouldn't have had the accumulating hail.
It's like a lahar.
Huh? Highway. And this actually hit highway, I think it's 287 in the Texas Panhandle. And they actually had to shut down the highway for a while because of all the accumulating hail and the flood waters and things like that. But you can just see these guys are actually having fun while they're out there. But I mean, you know, they were standing up next to 4-foot hail drifts that end up causing it. And Dual Pol was able to tell the forecasters that at that time. And if we go back, I mean, you can see reflectivity's high there, but I don't think it would have told me anything about the significance of the small hail that was going on. I mean, I don't know, maybe it does to you all, but it hasn't to me. I don't.
The fact that your KDP was, you know, over 4 or 5, you know, you had kind of constant hail, constant melting going on there.
Mm-hmm. And a lot of it, too.
How much of it reached the ground, how much it was accumulating, you're right, you can't tell that at this point.
Yeah.
But given the reflectivities and potentially probably the height of that storm, I'm thinking it was pretty decent.
Yeah. So there's what happened there. All right, let's move on to case number 5. And this is from Albany, New York. And so now we're going to go back up to the Northeast. So I'm trying to take you all around the country and just show you that Dual Pol is awesome everywhere. You know, it's not just in one location. But here we are in New York. It's towards the end of May. Here we've got a, you know, kind of an open trough over Canada that's, again, setting up southwesterly flow over the Albany area. Here it is, just again at 850 millibars, and you can see lots of moisture moving up into the area. Again, kind of a strong low over Canada. Looking at the sounding here, a lot fatter cape than what we saw with the Amarillo case. So you might be thinking, and especially in the hail growth zone, which is kind of the 0 to minus 20, got a lot of cape there, which is probably going to increase your large hail threat at this time. And here's just some SPC graphics. And for the SPC to go moderate in the Albany CWA or Albany area at this time, you know, pretty significant. They're thinking that stuff's going to be going on. So they've got a moderate risk. And here's what they were thinking. They thought kind of a tour, 5% tour over this area, but Albany is kind of in the 2% tour at this time. So they're kind of just on the edge of kind of the higher end tornado threat. This is the wind probabilities. They're thinking 45%, so you can almost imagine that they're probably going to get a wind event here. And then here's the hail threat, kind of a large area of 30% at this time. Now, it's not hatched, but again, it's still 30%. Pretty good probabilities. At this time, at the time that we're going to be looking at, there is a tornado watch out, and the area that we're going to be looking at is right here. So we're kind of right on the edge of the tornado watch. And there's also a severe thunderstorm watch out, although we're just outside there. I think it's right up in here. That's where we're going to be looking at. So again, you know, we're not in the severe thunderstorm watch, but we're very close to it. So, you know, again, we don't just draw boxes and say, okay, if you're outside the watch, who cares? You know, the environment is still fairly favorable. So here's reflectivity. What's reflectivity telling you? What kind of stands out to you? Huh? It's a big storm. Yeah, lots of high reflectivities. In fact, we're almost getting up to 70 dBz here in the low levels. Kind of got a little inflow notch. So maybe some supercellular characteristics at this time, but not your classic plain supercell that you would expect. Here's your velocity. In fact, let me go to SRM. I like SRM better. So, yeah, definitely a supercell. And in fact, if I were to show you upper tilt, you'd see that this rotation extends upwards as well. You've also got some storm top divergence aloft. So, I mean, this storm is cranking. It's going pretty good. Here's your Dual Pol. Here's your correlation coefficient. And co-located with that high reflectivity is a reduction in the correlation coefficient, and it's starting to get below 0.9 at this time. To me, that tells me you've got a large hail signature, and that you can be confident that you've got at least golf ball size hail occurring at that time. So if I go back to reflectivity, let me put it right there, put the cursor there. You can kind of see, let me go back. You can see it's kind of along that reflectivity gradient. And that's one thing to remember, is that sometimes your largest hail doesn't fall on the highest reflectivity, kind of falls on the inflow side of the storm and the reflectivity gradient. And that's what we're seeing here, is we're seeing that the largest hail is falling right in this area. But I can be confident, just looking at reflectivity and correlation coefficient, that I'm going golf balls. I'm going to say there's golf balls falling with this storm. And, you know, call it a day. No, just keep going. And then looking at ZDR, you know, your ZDRs aren't negative like what the typical values chart showed you here. But this is where I say that it depends on, you know, if all I had was large hail in there, I probably would see negative ZDR. But what I think is actually happening here is that I've got some large hail mixed in with some smaller hail, and the smaller hail is dominating the signal in ZDR, but the larger hail is dominating the signal in the correlation coefficient. So, you know, it's one of those things, you've got to look at all of the variables, all of the information, and kind of draw your conclusions there. And then here's your KDP, and you can definitely tell that there's some rain going on with this event, but not near as high as what we saw with the Amarillo case. And here's what happened. Actually, with that storm, we didn't get any reports. So I can't definitely tell you for sure that this storm did produce golf ball size hail, but what I can tell you is all the other storms in that area on this day did produce up to almost baseball size hail. We're talking 2.75 to almost 3-inch hail.
What about that dropout in KDP within that reflectivity?
Yeah, so right along in here. Yeah, that is another limitation that you have with KDP, is that when correlation coefficient drops below 0.9, KDP does not get computed because it's just too noisy. It's too noisy of a variable. And in fact, with correlation coefficient in general, the lower your correlation coefficients, the noisier your ZDR and your KDP are going to be, and the less trustworthy they're going to be at that time. So that's why you have the dropouts. Yes.
So where are you thinking? Okay, large. Just looking at correlation coefficient, large hail versus maybe debris.
I am thinking that this is large hail. That all of this is large hail. I'm not thinking any debris at this time, because let me show you here. Here's kind of the center of my low correlation coefficient, and if I step back up, keeping the cursor right in the same spot, it's not co-located with that velocity signature down here. So that's why I don't think that it's a debris signature at this time.
So there's a lot of information on that one cell there. How do you find your local offices, and especially the NextRad operator, handle multiple storms that are with this? I mean, it seems like a tremendous workload.
It is, and one of the things we try to tell them is look at the environment beforehand and kind of anticipate what you might be looking at, and then focus on the variables that are gonna indicate to you those threats that you're highly anticipating.
Hey, Clark, that's a rather broad rotation too, right? I mean, so you're not really looking at something focused and perhaps tornadic at this stage. But I'll reemphasize environment. I think that's key. Boundary interaction. If you've got an analysis that shows a boundary maybe just ahead of this storm, it's definitely one to keep an eye on for tornadic potential. Yeah, just knowing that background environment is so critical. You could have storms that all look like they've got great potential to be tornadic and dangerous, and only one or none may actually result in a tornado. And it's really going to come down to these fine-scale features in mesoanalysis that are going to help you.
Yeah, look at that Amarillo storm. That had a phenomenal hook on it.
Yeah.
And with the accumulating hail.
Yep. So there's case number 5. We've only got 2 more here. We're going to look at Hurricane Sandy. Now, Am I right in saying it's the Hurricane Sandy, or am I? I know it was a hurricane at once, so. But what we're going to look at here is here's the surface data at this time, and you can see kind of inland we're in the mid 40s, and as we get closer to the coast, it's getting warmer as that warm core low is moving on shore. Okay, and then if we go to the upper levels, I'm highlighting these three soundings because I'm about to show these soundings. I'm highlighting these three areas. What you can see is at 850 millibars, everything's still above freezing. You know, we've got 5 degrees Celsius here, 7 here, and 8 here. But you can see that it's warmer towards the coast, cooler toward as you go inland. If I go up to 700 millibars, now what you can see is that we are below freezing over here in the Stirling area, but along the coast we're still above freezing. So we don't have this nice just uniform height melting layer. We've actually kind of got a slope to it that we're looking at. So let me just kind of paint a different picture here. Here's the Stirling. So here, let me tell you, this is the Stirling area. This is going to be Wallops Island, and then this is going to be Upton up here. And so what I've done is I've highlighted where the temperatures cross the 0 Celsius height. You can see at Stirling, it's very low. If I step over to Wallops Island, you can see that it's increased quite significantly from Stirling, probably almost, you know, 3 or 4,000 feet. And if I go up to Upton, you can see that it's even higher there. And let me show you. And then what's actually kind of a little confusing here is that I tried to decide where I wanted to draw this. Was you can see there's almost an isothermal layer with the 0 Celsius here. So I had to be a little bit, you know, I just kind of take my own guess as to where I wanted to draw it here. But you can kind of see it's, again, it's a little bit higher. So here's the reflectivity. And what do y'all think is going on here with the higher reflectivities? And this is LWX. This is the Stirling radar. So, freezing level was, let me step back here. Wasn't too far off the ground. It was right at around a little above 800 millibars. So it's going to be very close to the ground. So a little bright banding there maybe. Okay. And then we go out a little further. What do you think's going on out here where you've got this kind of secondary enhancement in your reflectivity? Heavier precip, 2 melting layers. All right, let's go. We'll just skip velocity here. So here we've got correlation coefficient. And sure enough, this is a melting layer here. You know, very nice melting layer. But over that secondary enhancement, we do see a reduction in the correlation coefficient. And at the time, Paul Schlatter and a couple of us at WDTB were discussing this, trying to figure out what was going on, and we thought, oh, hey, cool. You know, one of the things with ice crystals is that if you get really pristine ice crystals, they can actually align themselves horizontally and then kind of flutter, and that can actually reduce your correlation coefficient a little bit. And so what we thought is we were seeing some dendritic growth out here. We thought, hey, we've already gone through the melting layer. We're above freezing now, so we think we're actually seeing a dendritic growth zone. We're like, hey, this is kind of cool. Well, then one of the other guys at work said, hey, why don't you pull up those soundings and actually see what's going on with the environment? And so we did, and we started looking, and we're like, hey, that may actually be a second melting layer or a higher melting layer. And sure enough, with Wallops Island being right out here, the melting layer was higher. And what we're actually seeing here is 2 melting layers. And just to kind of show it from a different angle, this is from the Dover radar, which is near to Wallops Island. You can see out here we see the bright band signature. But let me go to correlation coefficient. And this I think this just shows it a lot better, and it's easier to understand. Is that off to the west, where you had the cooler, the cooler air, much lower freezing signature or freezing level, you saw that the radar was intercepting that much quicker, so it was much closer into the radar. But out to the east, over the ocean, where the temperature was warmer, it wasn't hitting it as quickly, and so you can see that out here the melting layer is higher. So you actually kind of see that sloped melting layer effect, which I just thought was just really cool that you can actually see that kind of detail with dual pole here.
What were your elevations on those melting layers?
Let's go back here. This one looks like 3,500 meters, so I'd say, what is that, about 10,000, 11,000 feet? And then at Wallops Island, we're right around 3,000, so about maybe 9,000 feet there. And at Sterling, you're probably around 2,000, you're probably about 6,000 feet. So you're probably talking almost a 6,000 foot slope in the melting layer, just over that small distance there. So. But just some cool stuff there. But again, this is where I stress, know your environment when you're looking at the radar, because knowing your environment can definitely help you interpret what you're seeing on the radar. And then this is the last one here, and this one will be kind of easy. I want to end on an easier one. I want you all to guess where the meteorological echo is. So, and I'm just going to step through kind of a loop here of reflectivity, and you're going to see some interference spikes come up here. Sorry, that's not going to be the answer. So, but I'm going to step through. If you think you see non-meteorological echo, just stop me. So any guesses? I'll go back through the loop again. We'll go through it backwards here. Right here? Right here. I can step over here. So about right there.
Is that it?
Is that what you, looks a little, huh?
From there to the outer bank, right there.
Yeah, to right here. Yeah, that looks a little suspicious. Huh? This is Morehead City in North Carolina. Huh? Yeah, oh yeah, sorry, the radar site's right here.
Oh, that is an interesting signature southwest of them, too.
Where at?
Well, that one you pointed out, the banding, that banding southwest of.
Mm-hmm.
Yeah.
You confident in saying that that's non-meteorological?
No, that's, well, am I confident that that band there is non-meteorological?
Mm-hmm. Or this one here?
I'm not that confident with that one, but the one to the southwest certainly looks like a lot of noise.
So this stuff right here?
Yeah.
Yeah. Well, I'm gonna tell you that's just interference. So. Yeah. Yeah. That's from another radar. All right. So. Had a couple guesses. Good guesses there. How about velocity? You know, one thing in velocity is that non-meteorological, especially ground clutter, can show up as zero velocities. So, do y'all see any hint of that anywhere? Besides the zero isodop. That doesn't count. Anything? Yep. So nothing there. Okay. Correlation coefficient? All right. There it is. There. Where is it? Where do you see it? Yep, right there. Also right there. So yes, that low reflectivity was actually non-meteorological echo. But it extends inward into the core of the precipitation that was going on at this time. So let me go back to reflectivity here. See, I think it'll be easier to do it this way. So this whole area right here is a mixture of non-precip and precip echo, and this is mainly non-precip here along with that, but it's all embedded in the precip. But looking just at reflectivity, you know, it is lighter reflectivity, which means it's probably not going to be a heavy rain event that you're seeing at this point. But, you know, I couldn't tell that this is non-meteorological at this time. You know.
Tell your viewers that either.
Yeah.
You just just say, oh, there's showers.
Yeah, you just say, hey, I actually don't know. We don't know. In fact, I've talked to some of the people at Morehead City, and they don't know what was going on at this time, or nobody was outside looking to see if there were some birds or anything like that. Huh? Yeah.
Well, if you go back in the reflectivity, and the heavier cells down to the south, I don't know what they looked like prior to that, but was there perhaps any outflow boundary from previous convection?
Okay. Yeah, I don't know if there'd be strong enough outflow from that convection to really cause that widespread of a yeah. And then to be embedded in the precip, I'd expect that some of that stuff would get washed out. It wouldn't transport with the precip.
Some of the most puzzling radar signatures I've ever seen. I worked in a Wilmington office for about 2 years, and in the transition from when they had their 57 network radar to the Doppler, so we could look at both radars, and they were just the most remarkable radar signatures I think I've ever seen anywhere just offshore with the Gulf Stream. Some really interesting things happen out there, and not a lot of people around to tell you what's going on either.
Yeah. So, and I put here, I was trying to be an eye doctor here, better, worse, or no change. But, with correlation coefficient, it was definitely better. I mean, you could definitely tell what was going on. And let's just zoom in a little bit and just look at one image here. And this is that area where there was non-precip, but there is some precip mixed in. Does anybody want to take a guess to where the non-precip and precip is just in this little area? Where this light blue is?
Very light blue.
Mm-hmm.
I just saw that ring.
So we're at right in there. Okay. Mm-hmm. Yeah. Well, here's velocity. Again, probably nothing in the way of ground clutter that I can see here that would be non-meteorological. But here's that correlation coefficient. And I mean, you can see for the most part. Let's focus. I'm going to put my pointer right here. We'll go back to reflectivity. And sure enough, where you were saying there, where you've got kind of that lower reflectivity, it's non-meteorological. But I mean, if I were looking at that in real time, I might be thinking there's probably just maybe some drizzle, or if I'm thinking the rest of this is precip, I'm not going to think that this is non-precip here. If this was a little more isolated, I might be a little more convinced to it. But I mean, it's widespread. I might be thinking, just drizzle or light rain, but it's actually nothing there. But where we've got this higher correlation coefficient, that's definitely some rain. And where it's kind of noisier, it's probably, a mixture of, probably still some drizzle going on. But definitely in these very low correlation coefficient areas, it's non-precip. But just looking at reflectivity, I think it would have been a lot harder to tell at that time. So very cool stuff. And then ZDR was, in the non-precip areas were either dropping out or were very negative at this time. So, but I put on here, CC is your best friend. Always consult CC when you're trying to discriminate between meteorological and non-meteorological echoes. And then, like I said before, other dual pole variables will also look noisy when your correlation coefficient drops out. So, kind of the grand summary here is I say dual pole is cool. We saw anything from debris signatures to winter weather applications to hail applications, double melting layers, non-precip echoes. I mean, and this is just kind of skimming the surface of what we're seeing. And we're not done figuring out what's going on with dual pole. I mean, there's still a lot of things we don't understand that we're looking at doing research on to try to figure out what's going on. So dual pole is only going to get better as we go on. But it's already added confidence in what we're seeing out there. So I just want to mention the wdtb.noaa.gov webpage. If you're interested in any of the training, we've done a lot of dual pole training. One of the things I do want to mention is the storm of the months. Every last Wednesday, we get the National Weather Service people together, and we do just kind of a brown bag luncheon type thing where for 20 minutes we have a forecaster from the field submit an example, and then we just talk about it for about 20 minutes and just show how dual pole helped them in that example. We haven't opened it up outside of the Weather Service, but one thing we do is we record it, and then we archive it on our website, and you all are more than welcome to go view the recorded versions afterwards. And in fact, some of these came from the Storm of the Month. Some of the examples I showed today came from the Storm of the Months. So, I mean, you know, go hit those up, look at them, and just see what the field is learning. And we're going to keep doing those at least through the end of this year. So, but I'll open it up to questions now. Thanks.
This is Dave Jones with Storm Center. Are there any TV station radars that you know of that are going dual pole, or are they switching over as well?
I know there's some in the southeast. Barron has upgraded some in the Alabama, Florida markets. I know that there's been some dual pole upgrades there. And this actually brings up a really good point in that what I showed you here today is really just applicable to S-band or 10 centimeter radars. That when you start talking about C-band, 5 centimeter, and even X-band, that a lot of the logic is going to stay the same, but those values I was talking to you about, like the 0.9 for CC and large hail, is not going to be applicable at C-band or X-band because of how the dual pole interacts at those different wavelengths. But yeah, I mean, I know that there are some media markets that are starting to upgrade their personal radars to dual pole, but most of them are C-band.
Anybody here have any?
We have one in our market.
Yeah.
RAL has one too up in Raleigh. They've
Okay.
had one for a while.
Okay.
Cool stuff.
I was going to say, I know last year there was a AMS short course where we had somebody from North Carolina come up and show some cool examples.
And I would submit, I think that non-meteorological might have been chaff from the Naval Air Station there in
Okay.
Jacksonville.
Okay.
That would be my second guess besides smoke.
Yeah.
Okay, if there are no other questions, what I wanted to do is just to remind our online audience that at 1:30 we'll have Greg Carbon back and also Clark back to answer any specific questions from the internet audience. And so that should be quite exciting. It'll be 1:30 to 2 o'clock Mountain Time. So please come back and join the discussion. It's your chance to ask specific radar questions from Clark, the expert there. Bless you, Cindy. And also anything about the Storm Prediction Center from Greg Carbon. So with that, we're going to take a break for lunch and ending just a little bit early today, which is fine. And then tomorrow we will start again after you come back this afternoon, 1:30 to 2 o'clock. Tomorrow we'll start at 8 o'clock in the morning. So thank you very much, and we'll look forward to seeing you back here at 1:30.